In section 7.1, we're going to take a deeper dive looking at quadratic functions and their applications. And we're going to be hitting both SLL number 2 and number 3. We'll work on writing ax squared plus bx plus c in vertex form, that's sometimes called graphing form. We're going to apply quadratic functions in real-world situations. We'll construct the equation of a function given the graph. We'll graph a quadratic function written in vertex form. We'll graph and analyze quadratic functions. And then we're going to determine the vertex, axis symmetry, domain, and range of quadratic functions. So we'll start out with a definition of a polynomial function. A polynomial function f of degree n is in the form of f of x equals a sub m x to the n plus a sub m minus 1 x to the n minus 1, so on and so forth, plus a sub 1x plus a sub 0, where the variable n is a whole number, a sub 0 through a sub m are real numbers, and a sub n does not equal 0. So when we talk about a polynomial function, we're talking about a bunch of terms where the powers of my variables are whole numbers. 0, 1, 2, 3, 4, 5. So we can't have any fractions, any decimals for exponents. We can't have any variables in the denominator. The term a sub n, x sub n with the highest power is called the leading term. The coefficient a sub n of the term with the highest power is called the leading coefficient. A quadratic function standard form is a function written in the form of f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. The graph of quadratic function is called a parabola. The vertex is always either the lowest point or the highest point on the graph, and the vertical line through the vertex is called the axis of symmetry. It is where we can fold the graph paper so both halves of the parabola coincide. The coordinates of the vertex is h comma k, and the axis of symmetry is x equals h. So here are some properties of graphs. They're written in a times x minus h squared plus k. Notice that's kind of the same form we were using when we were graphing back in section 6.1. So a here would stretch or compress my graph if depending on the value of a. And if it's negative, it also would reflect it across the x-axis. My graph would be shifted horizontally h units and vertically by k units. So the vertex is the point h comma k. The axis of symmetry is the line x equals h. If a is greater than 0, the graph opens upward. Think of it as a smiley face. The k is the minimum value of the function. If a is less than 0, the graph opens downwards. Think of a frown. That's now my top point. K is the maximum value of the function. So here's kind of a visual picture of what's going on. When a is greater than 0, I get a parabola that looks like this. Here's my axis of symmetry, x equals h. This is my vertex. Notice that's the lowest point, or minimum point. And k is going to be the lowest y value. If a is negative, then my graph is reflected upside down. So now this vertex is the maximum point. The axis of symmetry does not change. And k here would be the highest value, or highest y value. So let's go ahead and take a look at work problems 1 through number 4. And so here they kind of did a little quick summary for you in the workbook. So with problem number 1, we want to look at the graph of f of x equals x minus 3 squared minus 9. We want to identify the vertex, x and y intercepts, the axis of symmetry, also state the domain and range in interval notation. So first of all, we know it's a parabola. And if we think about what we did back in section 6.1, we can shift it 3 units to the right and 9 units down. So it's my parabola. We're going to shift 3 units to the right and down 9 units. My vertex here is h comma k, so h here is 3, k is negative 9. Remember, h is going to be the opposite here. This is minus h, so I have to take the opposite of that sign. That means my vertex is 3 comma negative 9. So if you think about in terms of graphing, let's kind of put this together. If I go back to my transformations, here's my parent function. And I've got these points here. And I'm going to shift them. So 0, 0, I shift to the right 3 and down 9. So now notice that matches my vertex up here. This point at 1 comma 1, we shift right 3 down 9. This point negative 1 comma 1, shift right 3 down 9. Some other points up here, we would have 2 comma 4. So I'm going to shift to the right 3, down 9. And then likewise, I have another one at negative 2 comma 4. I'm going to shift right 3, down 9. And then I can start sketching in my graph. So notice this does match my vertex here. Now from the graph, it looks like my x-intercepts are 0 and 6. Let's just verify that. If I plug in 0, this is a negative 3 squared is a positive 9, minus 9 is 0, that works. If I plug in 6, 6 minus 3 is 3, 3 squared is 9, 9 minus 9 is 0, that also works. So I can read off what my x-intercepts are. The point 0, 0, and the point 6, 0. And that 0, 0 is also going to be my y-intercept. My axis of symmetry is going to be this line that goes through the vertex. Well, my h here is 3, so it's x equals h, so it's x equals 3. Now, do not just write down 3 for the answer, for the axis of symmetry. That would be wrong. It's the line x equals is 3. You need to write that whole thing down, that because it's actually representing the line x equals 3. In terms of our domain, my domain here is going to be all real numbers. In fact, for all these, unless it's an application, anytime you're working with a polynomial function, its domain is going to be all real numbers. Now my range, going from the bottom to the top, it starts here at negative 9 and goes on forever. Let's go ahead and try the next one. So now we want to graph f of x equals negative x minus 2 quantity squared minus 1. And I'm kind of doing the same thing. So my transformations, we do have a reflection. So this is reflected vertically across the x-axis. And let's see, well, we have this negative 2, so my h here is 2, my k here is negative 1. So it's going to be shifted to right. So let's say right 2, and down 1. So again, think about your parent function. Think of 0, 0. I'm going to reflect it, so this is now upside down. And I'm going to shift it 2 units to right and down 1. 1, 1, reflected, shift you 2 units to right and down 1. Negative 1, 1, reflected, shifted 2 units to right, down 1. And so my picture, it's going to look something like this. So my vertex should be 2 comma negative 1. Notice that does match that point there. Notice that it does not intersect the x-axis. So in terms of my x-intercepts, there's none. Looks like we have a y-intercept of about negative 5. Let's verify that. If x equals 0, this is negative 2 squared is 4. The opposite 4 is negative 4. Minus 1 is negative 5. So that does turn out to be the y-intercept. My axis of symmetry, x equals h, so h is 2, so it's going to be x equals 2. The domain here, it's going to be all real numbers. For my range, though, this goes on forever to negative infinity, so it's from negative infinity to negative 1. Remember, always write from smallest to largest, bottom to top. All right, let's take a look at number 3. This time we're given the graph and we want to find these things. So we've got the graph. So my vertex is this point here. That's 3 comma 4. My x-intercepts are here and here. So 1 and 5. Again, to make Alex happy, we'll write 1 comma 0 and 5 comma 0. My y-intercept here looks like to be a negative 5, so that'd be the point 0 comma negative 5. Axis of symmetry, it's right there, so that's x equals 3. My domain, it's going to be all real numbers. And my range, goes from negative infinity, tops out here at 4. And now they ask us to write the equation of the function. So remember, my form is y equals a times x minus h squared plus k. Remember, h and k come from the vertex. So h is 3, k is 4. So I can at least plug that in. I guess I should probably label this f of x. So that's x minus 3 squared plus 4. And now, we don't have a stretch here, but we do have a reflection. Since we have a reflection, that means a has to be negative. And so this would be our function. All right, let's turn the page. Let's go do this next example. So here we're doing the same thing. My vertex, negative 1, negative 8. So in fact, in terms of writing the equation, we almost have it. Here my h is negative 1. My k is a negative 8, and we'll have to clean this up in a minute. Really, the only thing I need to do is get my a value. And we can get that pretty quickly because I'm looking at this point, and if I go over 1, I only go up a half. So this is going to have a vertical compression of 1/2. And let's go ahead and clean this up. It's 1/2 x plus 1 squared minus 8. So I really don't need to do this other parts just to get the equation. So if I was only asked to do the equation, I would stop here. But that's not what they asked us to do. They want us to find this other stuff. So x-intercepts, we have one at negative 5 and one at 3. So it would be negative 5 comma 0 and 3 comma 0. Y-intercept looks like about negative 7.5. So I'm going to write 0 comma negative 7.5. Axis of symmetry is going to be x equals negative 1. Domain here is all real numbers. Range here starts at negative 8 and goes on forever.